Hello everyone, I hope you are doing well. So in today's video, we'll go through the 2018 physics exam for the Northern Hemisphere part 1, where we'll be going through question 1 to 9. And if you want the other questions, the other parts, it'll be in part 2 in the future. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. A 1,500 kilogram weather satellite is in circular orbit around the Earth at an altitude of 850 kilometers. The radius of Earth is 6,400 kilometers. Calculate the period of the satellite in seconds. Take the mass of the Earth to be this and the universal constant to be this. Show your working out. Not too bad. So, what do we know? So let's have a draw diagram of what we know. So, if I draw Earth as a circle, and let's say I draw a little satellite like this. So we're actually given that the altitude is 850 kilometers, which you remember altitude's this over here. It's from the surface of the Earth to the center of the satellite. But remember, we want the orbital radius for calculations. Orbital radius is, remember, the distances between the centers of those two masses. So all we have to do is actually just add the radius of the Earth. So we will have now the orbital radius. So the orbital radius is just the addition of the altitude and the Earth, the radius of the Earth. So let's do that. So 850 times 10 to the power of 3 to make it to meters plus 6400 times 10 to the power of 3, and this will give us to meters, it gives you 725,000 meters. Actually, let me write that nice, 0 meters. So this is your actual radius or orbital radius, and now we're just going to use one of Kepler's law to find the period. So we know about Kepler's law. Let me open up my summary sheet and really find out what the formula is. So Kepler's law, here it is. Kepler's law states that, this is what Kepler's law is, r to the power of 3 divided by t squared is equal to gm 4 pi squared. What we really need is the period, so we need to make the period t the subject. So what I will do is I will flip everything around, so t squared over t to the power, r to the power 3 is equal to 4 pi squared all over gm times both sides by r to the power 3, so we just get t. So t squared equals 4 pi squared r to the power of 3 all divided by gm, and I square root both sides, so we get t is equal to your square root of 4 pi squared r to the power of 3 over gm. So this is your formula, so let's put that there. So t is equal to the square root 4 pi squared r to the power of 3 all over gm. And that's it, we've got our formula. And now let's sub all those values in. So 4 pi squared times your radius, your orbital radius, which we just found that it was 725,000 to the power of 3, all divided by your g value, which is 6. Make sure you use their one, so it's 6.7 times 10 to the negative 11 times your mass of the Earth, the central mass, which is the mass of the Earth. 6.0 times 10 to the power of 24. So putting this in your calculator, we should get the period. And we want to make sure it's two significant figures, because that's our lowest significant figures. 4 pi squared times 725,000 0 to the power of 3, 6.7 times 10 to the negative 11, 6.0 times 10 to the power of 24. So that gives me the two significant figures. Let's have a look at that. Have I written everything nice? So yep, to the power of 3, beautiful. So enter that, and that gives me pretty much 6.1. So 6.1 times 10 to the power of 1, 2, 3. 3. So 6.1 times 10 to the power of 3 is your pretty much your period. Looks good. Question B. The controls of a satellite use its motors to move the satellite into a higher orbit. So if we're going to a higher orbit, we're actually increase your radius. We're increasing our radius, orbital radius. Will this increase, decrease, or have no effect on the speed of the satellite? And justify your answer. So, all right, let's have a look at this. Let me just rub this part here. We know that velocity is, to calculate the velocity, of course, the velocity is the square root of gmr. Where we can see that, there is this inverse proportionality. So, for example, if you increase your r value, so you increase your orbital radius, it will have a decrease in your velocity from the formula. So we know that velocity is actually inversely proportional to the square root of r. That's the actual thing that we can pull out from it. So if we increase, to a higher orbit, it means if we increase r, we know straight away velocity should decrease from this formula. And when you're trying to do questions like these in, say, exams, you want to make sure you put the formulas in. So where did you get, where are you getting this relationship? I got it from here. And yeah, so let's try to write for 3 marks. Wow. So what I would just write is, okay, using v is equal to the square root of gmr, we know that v is proportional to 1 over square root r. That's, I think that will give a mark. And let's explain. We can see that if we increase the orbital radius, the velocity decreases. Due to the inverse relationship. So to the inverse between velocity and between velocity and radius. And I think this pretty much does explain everything. That's it. So it does decrease. Easy. Question 2. Will this increase, decrease, or have no effect on the gravitational potential energy of the satellite? Take the surface of the Earth as zero gravitational potential energy. Justify your answer. Now, a lot of students, you would use, gravitational potential energy is GP is equal to mgh. And they'll be like, because of the radius is increasing, your height's increasing, hence your gravitational potential is increasing. Be careful. Do not show this. And here's why. This formula, we only use it when we're at the surface of the Earth, because we know that G is uniform. It's always the same on the surface of the Earth. But whenever we know that as we go above and beyond the Earth, we know that G, changes and it becomes non-uniform. So you really cannot use this formula. So, all right, if we cannot use this formula, how can we explain this question? Well, in my mind, the best way that I would explain it is by energy conservation. For example, if I draw Earth here, and I draw that, satellite. Yep. And of course, we're taking distance from here, and the surface, of course, the surface of the. Let me actually move this nicer, like that. Okay, so we know that the surface is where. Think of it as like a ground, and so we know at the surface they told us that the gravitational potential energy must be 0. But we know the total, the total energy, the total mechanical energy, which includes both the gravitational and the kinetic energy, should be a constant value. So if GP is 0, we know at the bottom the kinetic energy must be at its maximum value. But as we go above and above, like up, what happens? We know that some of the kinetic energy is going to decrease, and because we know as we go higher, as R increases, what do we know? Velocity decreases. And remember, kinetic energy is proportional to velocity. Whatever happens to velocity, if we have 0 velocity, we have no kinetic energy. If we have higher velocity, we have high kinetic energy. And from that relation, as we're going higher and higher and higher, what do we know? Our, velocity is decreasing, hence our kinetic energy is decreasing. So what's happening to all that loss of, kinetic energy? It is being transformed to gravitational potential energy, because remember, you still have adding these two here must equal to whatever is here. If they must equal to a constant value. The total energy must be constant. So the loss of kinetic energy as you're going higher and higher is all being transformed to gravitational potential energy. So the higher you go, the higher the R value. So the higher the radius, the orbital radius, the higher your gravitational potential energy will increase. That is how I would have explained that. So let's now write a nice one. So what I'm going to say is since the total energy is constant, which is equal to, of course, your gravitational potential energy plus your kinetic energy. From the from the previous question, as the orbital radius increases, we know that velocity decreases. So hence your kinetic energy must also decrease, of course. So hence your kinetic energy decreases as we know that, as the radius. Okay, that's one. I think that's it. And then this results in your gravitational potential energy. So this results in gravitational potential energy increasing as the radius increases, because the total energy must be constant. I think that does define what happens here. Since the total energy is constant from the previous question as the orbital radius increases, we know that the velocity decreases, hence kinetic energy decreases. This results in GP increasing as the radius increases because the total energy must be constant. I think that is a beautiful, explanation. Question 2, let's do this. The electrical gun section of the particle accelerator accelerates electrons between two plates that are 10 centimeters apart and have a potential difference of 5,000 volts between them. Okay, so we're also given the mass of the electron and the charge of the electron. Calculate the electrical field between those two plates, include an appropriate unit. So straight away, when I'm looking at two plates, parallel plates, the formulas that come to my mind, having a look at my summary sheet, is for parallel plates is V is equal to ED. Where, of course, we want to calculate electrical field, so that's our E over VD. And so our voltage in this case is, of course, 5,000. Dividing it by your distance, make sure it's in meters. So 10 times 10 to the negative 2. And so that gives me 5,000 divided by times 10 to the negative 2. It gives me, we want it into two significant figures. So it gives me 5.0 times 10 to the power of 4 to the power of all 4, and of course we want the units. So for the units, of course, it's volts per meter from the formula, volts per meter. And yes, that looks good. Next question. Let's have a look at the next question. Calculate the magnitude of the force on an electron between the plates. So what we want to calculate is the electrical force. And so to calculate the electrical force, it is force is equal to Q times your electrical field. So, which in this case is, because what's our charge? It's an electron, which is 1.6 times 10 to the negative 19, was it? Yep. Times your electrical field, which we just calculated, 5.0 times 10 to the power of 4. So putting that all again, so 1.6 times 10 to the negative 19. That gives me, to two significant figures, 8.0 times 10 to the power of negative 15. Beautiful. Question C. Calculate the speed of the electrons as they exit the electron gun. Ignore any relativistic effects. Assume that the initial speed of the electrons is 0. So straight away, remember guys, the electron gun formula. To always calculate the speed, we use the electron gun formula, which is half mv squared is equal to Q times your velocity. Your voltage, my apologies. So I want to get, velocity as my main subject. So what I'm going to do is multiply both sides by 2. So I can get, rearranging it will just give me velocity is equal to 2qv over m. Is that right? So 2, yep, divided by m. Good, and take it, sorry, beautiful. So using this formula over here, by rearranging it, I just have to sub in all the values. So of course it's 2, your charge, which is 1.6, times 10 to the negative 19, times your voltage, which was 5,000 volts. Let me double check again, is that right? Yep. Times your mass. And so your mass is 9.1 times 10 to the negative 31. Yep, 9.1 times 10 to the negative 31. So let's sub that in and find out what happens. So to two significant figures, that gives me 4.2 times 10 to the power of, so 1, 2, 3, 4, 5, 6, 7. 4.2 times 10 to the power of 7. Beautiful. Question 3, let's have a look at this one. A uniform electrical field accelerates protons from rest to a speed of this. Alright. So we're given the mass of a proton and the charge of a proton. The protons then pass into a region of a uniform magnetic field that is right angle to their velocity. They are bent in a circular motion. Explain why this path is circular in shape. What a beautiful question. If you guys don't know, of course, you will have to go through a circular motion. Think of it like this. If we have, say, a magnetic field that's into the page, circular path that goes into the page, something like this. And say we have like a nice, proton that's going at a velocity, so P positive. So this is your proton. We know that when we have, say, for example, a velocity and so the path of it, so the velocity and the magnetic field, there will be a force produced because they are perpendicular to each other. And the force that is produced is using your right-hand slap rule. So putting your fingers right into the page, because that's where the magnetic field goes, and your thumb to the direction of the velocity, we found out that there is a force downwards. And so think of it like this. This force downwards is right downwards. This is your force. This is your centripetal force. Meaning that there's a force that's being pushing it downwards. So the actual path is going to go like this. The electron's going to go here and somewhere over here. Now, what's going to happen here too? Let's think about it. Again, using, of course, now the velocity is over here. Again, using your right-hand slap rule, you'll find that the actual force is going to be over here. Wait, so imagine this is your center. Can you see how, as much as the ball is going, now the velocity is going to go here. Imagine this is your velocity. And again, using your right-hand slap rule, you'll find that the force is going always towards the center. So what's going to happen is it's actually going to go through a circular path because the velocity, the speed is constant. But yeah, the force is always changing in this circular motion. And that's why it's actually creating this uniform circle. And yeah, because the velocity is not changing. Of course, the velocity is constant. The speed, not velocity. Velocity changes because there is a change in direction. But what we're talking about is the speed is constant. And that's why there is always this force that's being produced, the centripetal force that's being produced always into, towards the center of the circle. So it's just going to go through this circular path. I hope that kind of easily explains what it is. And yeah, let's now write. How can we write this? So question 3a, let's do this. All right. So what we're going to say is, because I'm going to write, so we're going to say when a, so let's try this. So when a charged particle, moves through a magnetic field, perpendicular to its velocity, it experiences a force perpendicular it experiences a force perpendicular to both its velocity. So to both its velocity and magnetic field direction. And magnetic field direction. Alright, so that does explain where there is a force produced. And so this force, is known as the centripetal force. So I think here just kind of summarizes what happens, but we haven't really explained why there's circular paths. So this, I think, would give you a mark, being very specific in what force that there is a force produced. So I will put that there right now, and so I'm gonna put this at the bottom of this over here, and I'm gonna give another dot point because I think I'm gonna write a very big one. Well, and of course in exams you don't want to write this big. I just want to be very like detailed in my questions so you can guys read them and understand what's happening. And yeah, so take only the important dot points from this. The next thing, the dot point I would say, is the centripetal force. The centripetal force causes the proton to move in a circular path. This circular path, so this circular path continues because the magnetic force continuously changes the direction of the velocity, as we've shown from the thing, keeping the proton on a curved trajectory. I think that trajectory, easy. So I think that's another part that we could pretty much, yep. So, oops, let me take this only pi. And I'll just give an extra dot point where I'll be more, the last final, I would say, we would say something like, alright, would say since the proton is moving at a constant speed, the radius of the circular path remains constant. And that's why we get this beautiful circle, remains constant, resulting in a uniform circle. That's it. I think that is pretty much, that summarizes everything of how a circle always gets produced in these kind of questions. And yeah, I would absolutely don't write the whole thing. This is not how you want to write it in terms of VCAR ways. Make sure to only read it and understand and take the only important parts from it. That's why I'm being very, I've written a lot so you can guys read them and fully understand how it's being produced. But of course, you just want to write 1 dot point for each. 3 dot points that specifically tells us what's happening. So let's do B now. The strength of the uniform magnetic field is 500 milliteslas. Calculate the magnitude of the magnetic force on the proton. So let's have a look at the formula sheet for magnetic force. Easy. So we know that the magnetic force is equal to Q VB. Alright, so your charge is your Q, and it's 1.6, it's a proton, so 1.6 times 10 to the power of negative 19 times your velocity, which here is 5.00 times 10 to the power of 7 times your magnetic field strength, so 500 times 10 to the negative 3 to get it in Teslas. So this should give us what? 1.6 times 10 to the negative 19, 5.00 times 10 to the power 7, that's 500 oops, 500 times 10 to the negative 3. And that gives me 4, so to 2 significance, 4.0 times 10 to the negative 12. All right, does that look right? Yeah, it looks good. 5 times. Have I made any mistakes? 1.6. Yep, every value looks good. And yeah, for 3 marks, wow, that's easy to get. Question 4. Let's have a look at question 4. Students move in a circular loop of wire of 100 turns into a cross-sectional area of this. The loop moves at a constant speed from outside left, as you can see from here. They're moving to the left, and then the left into throughout the magnetic field as shown. The area between the poles has a uniform magnetic field of magnitude this, and figure 1 shows the view from above. On the axis provided below, sketch the magnetic flux through the loop as it moves into, through, and out of the page. Easy, one of the most nicest, easier questions I kind of repeat every year. So this question is easy because, all right, so remember your magnetic flux we only generate magnetic flux if there is a magnetic field line that passes through the loop. A magnetic field lines that pass through the loop. So imagine you initially started over here, as we're saying here. Of course, there's no magnetic field lines that are passing through it, so we have no flux. So imagine at some time, we have no flux. So let's just draw a straight, constant line like that. Let me draw it nicely, actually. So like that. Beautiful. And so as the loop is going to start passing slowly, the field lines are going to start passing into it little by little, and so it's increasing in magnetic flux until it fully develops. It's fully into that magnetic field, and then of course your flux will be constant. So as it's passing inside, there'll be a flux that's going to be increasing. So there'll be a flux that's increasing like that. And then as it's, inside now the loop, now, the flux is constant because there is no change in flux anymore. It's just constant throughout. The field lines are all passing through. So it's going to be something like a straight line like that. And as it's at the end over here, as it passes out, of course, the, field, some of the loop is going to pass through here, and it's going to start decreasing in that flux because some of the magnetic field lines are going to be not going inside the loop anymore because it's going out of the magnetic field line. So it should be decreasing. And then it should go straight. As it's going more to the right, there's no more flux that's being generated. So it'll look like something like that. And yeah, easy. On the axis provided below, sketch the EMF induced through the loop as it's moved into, through, and out of the magnetic field lines. Easy. To do that, guess what it is? It's just looking at this over here and using the formula -n change in flux over change in time. Now, we don't care about n because we're just trying to have a look at the relationship. This change over here, this over here is actually the derivative. What it's telling us is if you derive this over here, wow, is that with respect to x? Oh, because it's respect to position, yeah. What it is if you derive your magnetic flux, for example, it's all about looking at the slope. So for example, here at the beginning, what's happening to the slope? It's 0. It's just a constant slope. So if you derive like a slope that's at 0, it's just going to be 0. So there will be no EMF produced because imagine this here is 0. Your EMF is going to be 0. And then here we have some change. Can you see how it's increasing? What is the gradient? We know that the gradient is positive because it's going up a slope. Good. So it's increasing, but be careful. Because we have a negative in here, we have to make... So if it's going up, it's going to go down. So it's going to have this downwards thing. And of course, in this part here, we know it's a constant. It's constantly increasing. So there's going to be a constant EMF that's going to be produced. And then as we reach this point over here, we're going back to 0. All right. Now we can see that the magnetic field, we can see that the gradient over here is at 0. So imagine you sub in 0 here. Of course, it's just going to be a 0 field. So it's going to, of course, we won't generate EMF. Because remember, EMF is only generated when there is a change in flux. So now have a look here. There is a change in flux, but it's negative because the slope is downwards. So remember, by negative, it's going to be a positive. So it's going to have a look same. It will look the same as this, but now that. And as it passes, of course, part of here, it's going to be 0. So that. A very typical question in exams, to be honest. I've seen this question quite a lot in practice exams I've done, and it's such an easy way to get marks. It really is. And yeah, that was a very easy explanation, and yeah. C. The loop takes 2 seconds to move from completely outside to completely inside the magnetic field. Calculate the magnitude of the induced EMF in the loop as it moves into the magnetic field. Easy. We know that the EMF is, we don't care about that negative, so forget about that because we want the magnitude. So N times your change in flux over change in time. So we now, how much was it? How many, do we have a value of N? Yes, we had 100 turns. So 100 turns times your change in flux. Remember, change in flux is the area times your magnetic field strength. So we know area from that part here is 4.0 times 10 to the negative 4. 4.0 times 10 to the negative 4. Yep, is that right? Good. And times by your magnetic field strength, which is 2.0 times 10 to the negative 3. 2.0 times 10 to the negative 3. Just want to double check that's right. 0.0 times 10. Yep. And we divided by the time, which we found that it is 2 seconds to go through the loop. So putting that all, we should get our flux. 100 times 4.0 times 10 to the negative 4. 2.0 times 10 to the negative 3 divided by 2. That gives me, wow, it's a very, very small number. So it gives me, to two significant figures, 4.0 times 10 to the negative 1, 2, 3, 4, 5. Negative 5 volts. That's actually, yeah, looks good. D. Determine the direction of the induced current in the loop as it moves into the magnetic field as viewed from above, clockwise or anti-clockwise. Justify your answer. What a beautiful question. What an easy mark to get it, easy full marks to get in this. This is an application of Lenz's law. So let's have a look over here. So this is what Lenz's law states. So here, imagine this is your, of course, this is your loop. And okay, so as it passes, as it goes to the right and, goes inside this magnetic field, what's going to happen? So by Lenz's law, this is what we want to say. The magnetic flux through the loop is going to be increasing because as this is going to go to the right, there is, field lines are passing through it. So the magnetic flux is increasing and it's increasing into the page, the direction of the, of the field lines. So by Lenz's law, the induced magnetic field will oppose this change in flux. So how, for example, let me explain it. So the magnetic flux is increasing into the page. So you have flux that's increasing, into the page. But by Lenz's law, the induced magnetic field will oppose this change in flux. So it will oppose it. The way it will oppose it is what? So it will actually change the direction. It'll be out the page because it's going to try to oppose that change. Because remember, there was a change in flux into the page. So the way it opposes it, it creates a induced magnetic field that will oppose it by, out the page. And guess what? We use our right hand grip rule or coil rule. And so your finger is going to go to the direction of the magnetic field, which in this case is out the page. And you should look at your fingers, so your fingers curled up and see what direction they are. So from my fingers, I can see that they are actually moving this way, which is anti-clockwise. And so this is going to be your induced current. And it flows through anti-clockwise. And that's it. You just need to explain it in a nice way. This is what you do. These questions are very nice because in exams, they're very repeated. So let's write. This is all you're going to write. We just write the magnetic field. The magnetic flux through the loop. So through the loop is increasing into the page because it's going into the page. Beautiful. By Lenz's law, the induced magnetic field will oppose this change in flux. This change in flux. So it will be directed out the page. Easy. And then last question, you know, using your right hand grip rule, using the right hand grip rule or call rule, grip rule. So right hand grip rule, the induced current will flow anti-clockwise from what we saw. Clockwise. And that's it. That should give you full marks. 3 marks, 3 dot points. Beautiful. Question 5. Let's have a look at this one here. Students construct a model to show the transmission of electricity in transmission lines. The apparatus is shown in figure 2. All right, we're given this, a power supply, wires. All right, and we're given some transformers. The students use 2 transformers, T1 and T2, with ratios 1:8 and 8:1 respectively, and a 2-volt RMS AC power supply. Assuming that the transformer is ideal, so there's no power loss, the students use a light globe that operates correctly when there is 2 volts across it. So this light globe only works when there is 2 volts across it. All right. The wires of the transmission lines have a total resistance of 4 ohms. All right. The student measures the current in these wires to be 0.5 amps. So the current that's running through these wires, let me use a different color so you can see it. Like that is 0.50 amps. All right. Calculate the power loss in the wires. What a beautiful question. So we know power loss is just I squared over R. And so your current that's running through those transmission lines in those wires is 0.50 squared times your resistance, which is 4. We found that. And so putting this in your calculator, what do we get? So 0.5 squared times 4. That gives me 1. So to how many significant figures? The lowest is actually just 2, so 1.0 watts. 1.0 watts of, that'll be lost. Calculate the voltage across the light globe. So we wanted the voltage here. We want the voltage that runs to this white globe here. So remember, this is not the voltage that's running through it. This is the amount that it needs for it to work properly. But what's the voltage that is here? Well, the way we calculate that is how? Well, we have to start from the beginning actually, because, all right, so the way we're going to do this is, okay, we start with, let me draw a nice and actually simpler model to model this. So imagine this is your AC. This is your AC that's creating your 2 volts RMS, so 2 volts, and it's these current wires are going, and they're going into a transformer. And this is your first transformer, which is your T1, and it has a 1:8 ratio. And so, you know, we have a resistance, so put a resistor, and that's your Y's, of course. And that has 4 ohms of resistance. And as it passes, we have, of course, another transformer, which is your T2, and it passes through our light globe, which is just right like that. This is your light globe signal, and yeah, that's a nice, and of course that's an 8:1 ratio, and we know the current that was running through these wires are 0.5 amps from the question. So taking all this information, let's take all this whole diagram, and this is going to just really help us do all these calculations in a second. So let's leave it there. So we want the voltage that runs through here. This voltage that's going to go to this lamp. So the way we would do it is, okay, if we have 2 volts over here, 2 volts, we want to first find how many voltage are going to be in this output. So, you know, of course, in this input, it's just going to be 2 volts because that's the only thing that is, you know, being produced. There's nothing. So it's only 2 volts in this primary, and we want to find, we can easily find the secondary, what comes out in the secondary output voltage of this one over here. So what I would do is, okay, we know that VP is equal to VS is equal to, of course, we have the number of course, so it's going to be NP over NS. And so, and this is for, of course, T1. This is for, you know, T1, of course. And so putting all this, what's your primary voltage? It's 2. We want to find our secondary voltage, and it's a 1:8 ratio. So your voltage S is 16, actually, 16 volts. So in here, over here, in what will come out is 16 volts. Now, what's going to happen is, of course, we have a resistor here that's going to consume some of that voltage. And how do we find that? That's going to be easy, because we know by Ohm's law that voltage is equal to current times your resistance. Because we know the current that runs through it, so your voltage is just your current, which is 0.5, and your resistance, which is 4. How much would that be? So it actually will just become 2 volts. So this will consume 2 volts out of that 16 volts. So what would be left out? There will be left out of 14 volts. So if this consumes 2 volts, the left out ones, that's going to go to this transformer, it's going to be only 14 volts. And so again, we use the ratios, but in now T2. That's going to give us our output voltage over here that goes to that lamp. So again, so we're going to write VP, VS, MP, and S. So your voltage, your primary voltage is going to be, of course, 14 over VS. It's an 8-to-1 ratio. So it's going to be 14 divided by 8. It's just going to be 1.75 volts. Your secondary voltage is 1.75 volts. So this over here will receive, the actual lamp will just receive 1.75 volts, which is not enough actually. Which is not enough because we need 2 volts. So yeah, but that's your voltage that runs across that light globe. It's just 1.75 volts. Easy. 4 marks, wow. Question C. The light bulb does not operate correctly as it should, with the voltage supposed to be at 2 volts across it. Describe one change the student could make to model to make this light operate correctly. Well, of course it wouldn't operate correctly because it's only 1.75 volts. We're not getting 2 volts into this. There's many ways you can change it, but I think the most basic way that's coming to my mind is actually just changing these ratios for the T2. Because what we can do is, we want 2 volts, yeah? We want 2 volts to come, to the secondary voltage. And so, we want 2. And if 14 volts are coming to the primary voltage, so 14 volts, what should this be here? Because remember, it's a step-down transformer. So we're going to keep this as 1. Your N S is just going to be 1 because, you're stepping it down. But what about your N primary? So this one here, we can change it. So NP is what we can maybe change. So let's put it as X. That's what we want to find. So yeah, we can change the ratios for us to, give us a more higher voltage. So that's what we're going to use these ratios, and let's try this out. So so it's going to be, of course, VP, VS is equal to your MP over NS. So it's just going to be 14 over 2 divided by your X over 1, which is just X. X is just 7. So if we put this to 7:1, if I just put this ratio to 7:1 and change the transformer from a ratio to 7:1, we should be able to produce an output voltage of 2 volts, and then this would run correctly. There's many ways you can do this, of course. You can actually, for another fact, you can, for example, we can replace the transmission line resistance. We can do that, or we can change this, step up transformer voltage, or we can actually even change the voltage, from this power supply. But I think the most easiest would be this one over here. Just change this over here to give us that, because we've done all those calculations. Why make your life more miserable? So it's what we can say is, I think, all right, let's do it here. So just 2 marks. So we can say, is one change. So change the T2 transformer. So change the T2 T2 transformer ratio actually to 7:1, and that should make it correct. And we'll just give one more for explaining it. So this changes. This change in ratio will result in an output voltage of T2 transformer to be 2 volts needed actually for the globe to operate correctly. It's for the globe to actually, yeah, to function properly. Function. All right, I think that will be here. That looks nice. Yep, one change. All right. Yeah. So let's go down. Question 6. Yes, projectile motion, one of my favorites. A rock of mass 2 kilograms thrown horizontally from the top of a vertical cliff 20 meters high with an initial speed of 5 meters per second as shown in figure 3. Calculate the time taken for the rock to reach the sea. So we want to calculate the time. I mean, we're given a lot of information in terms of the vertical, direction. So what we can do is, yeah, use our vertical the vertical way to solve this for our time, because we know that the vertical initial speed is 0, because remember there is only horizontal that is 25. What about the vertical? It has to be 0 because there is no vertical horizontal velocity. We know, of course, acceleration is negative 9.8 in the vertical direction, and we also know that the s, your displacement, is going to be negative 20. Remember, because it's going down, and it's 20 meters when it hits the floor. And so we're just trying to calculate here is the time that it takes. Easy. So the formula that comes here is s is equal to ut plus half at squared. And so if s is negative 20, of course, u is going to be 0, so it's just going to be half a, which is negative 9.8 t squared. So let's calculate t now. So what's going to happen is 20.5, 1.8, and then take the square root of that. So your t value, how many significant figures do we want to give it? To 2. So the t value is just going to be 2.0. 2.0 seconds. Wow. Easy. Calculate the horizontal distance from the base of the cliff to the point where the rock reaches the sea. So we want this horizontal distance, of course. So the way you do that is, because we have the time, which makes our life easier, all we need to do is, we know that distance is equal to velocity times time. And so your distance in the horizontal velocity is, of course, the velocity is constant. It's always 25 in the horizontal direction. So it's just going to be 25 times 2, pretty much. So for my answer. And so that's going to be times that. So sorry, 2.0. Let me write that. Times that with 25. We get two significant figures. That gives me 51 meters. Yep. Because remember, you have to use, be careful, I know it's 50, it looks like 50, but you need to use whatever is in your CATs. For example, the actual real time that I was getting, use your exact value in your calculator. So my exact value was 2.020. So my actual time is 2.02003, blah, 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 blah. And I used that in my calculator, then times it by 25, and that gave me approximately 51. Two significant figures. Easy. E. Calculate the kinetic energy of the rock as it reaches the surface of the sea. Show you're working out. Easy. So we actually need to calculate the velocity. The velocity as it, so say it reaches here. Of course, it hits the floor here. So its velocity is going to look something like this when it hits. It's going to look like something like this when it, hits the floor. And we want to calculate that velocity. To do that is we need to break it down to its components. We're going to have, of course, 2 components. We're, of course, going to get that 25 meters per second from the horizontal, and it doesn't change. But what about your vertical? The vertical, of course, changes. So let's calculate that vertical component. To calculate that vertical component, we have to use some of our formulas. So what I would do is, because we know u is equal to 0, a is equal to negative 9.8, and we want to calculate v, and of course s is negative 20. The formula v squared equals u squared comes to my mind. So v is just square root of 2. Your a is negative 9.8 and s is negative 20. So putting that should give me your velocity in that direction. So that gives me a velocity of 19.79 meters per second in the horizontal. So of course we're going to use Pythagoras theorem to calculate velocity. So using Pythagoras theorem, which is just your square root. So your velocity is just going to be square root of 19.79 squared plus 25 squared, and that's going to give us our velocity. And I got it. So let me rub this out from here. So your velocity is actually just 31.89. meters per second. So to calculate the kinetic energy, we remember EK is equal to half mv squared, which is half your mass. What's the mass? 2 kilograms times your velocity, which is 31.89 squared. And that's going to give us what? Let's calculate that. It gives me a 1017 joules of energy. Beautiful. 1017 joules. Done. Question 7. Let's also do this one over here. Students are studying the behavior of a golf ball hitting a golf ball, treating it as a collision between the head of the golf ball and the golf ball only, as shown in the... So a golf club on the golf ball is shown in figure 4. The students take these following measurements. So mass, we're given the mass of the head of the golf club, the mass of the ball, initial speed of the golf club, the final speed of the golf club. Okay, the ball is stationary before it was hit. All right, and the ball's speed immediately. So the ball speed immediately after being hit is 63 meters per second. Use calculations to determine whether the collision is elastic and inelastic. Show your you're working out. What a beautiful question. This question is every exam that you do, practice exams, there is always one question like this, always. And it's one of the most easiest marks to get. It's approximately like every time it's like 3 marks to get. So let's do what we have to do. Well, for us to show that it's elastic or inelastic, for it to be elastic, the initial kinetic energy must equal to the final kinetic energy. For example, the initial, so EK, initial, so like I'm going to write I, must be equal to your... Let me actually write it because I think you wouldn't want to write it like that. So I'm just going to write it as the initial kinetic energy must be equal to your final kinetic energy for it to be elastic. That is the condition. If they're not equal, they're not elastic. That's the way we do this question. So let's calculate the initial kinetic energy. Easy. So the initial kinetic energy, of course, is going to be half. Well, of course, the mass of the head of the golf club. So it's going to be 0.50 times your velocity squared. What was it initially going? We know that the golf club was... The initial speed of the golf club was 45 squared plus... Now, what about the initial speed of the... So the initial kinetic energy of the golf ball plus... So the mass of the golf ball is 0.040 times your velocity. We know the golf ball before being hit was stationary, so it's going to be just 0 squared. So that's just going to be 0 anyway. And this is your initial kinetic energy. So let me write that here. Just over here. Let me write it like that. So this is your... Oh, wow. I need to a little bit make more space here. I'll write it here. So your initial kinetic energy is equal to that. And so putting in our calculator, we get... We get around 506.25 joules of energy. Now, let's calculate the final. So the final kinetic energy is just going to be half. So, so this is for the golf club. What's the final velocity of the golf club? It stated that the final speed of the golf club after hitting the ball is 40. So 40 squared. Plus, what's the kinetic energy of the golf ball? 0.040. After being hit, what's the speed of the golf ball? It says the ball speed after being is 63 squared. So writing this all down, 0.5, 40 squared plus 0.5, 0.040, 63 squared. This gives me 479.38 joules. Now, they're both not equal. The initial kinetic energy is actually not equal to your final. Hence, this is an inelastic collision. So, initial kinetic energy is not equal to your final kinetic energy. Hence, this is an inelastic collision. That's it. Beautiful. Question 8. Let's do this. let's use this color. In an experiment, a ball of mass 2.5 kilogram is moving in a vertical circle at the end of a string as shown in figure 5. The string has a length of 1.5. Calculate the minimum speed that the ball must have at the top of its arc for the string to remain tight under tension. What a easy question. So whenever they give you whenever it's like vertical speeds, we always get like to calculate the minimum speed, and that's what VCA has been doing for quite a long time. And there's only one formula to do that. It's always this formula: V is equal to square root of RG. Whenever you get some circular motion, especially like a ball or something, and they tell you to find the minimum speed at the top of something, it's normally this formula that we use. And it's very easy to transpose, but yeah, because it's only 2 marks, you don't want to waste too much time on that. So V equals square root of RG, where your velocity is the square root of your radius, which is 1.5, and your G. 9.5, G is 9.8. And we want to do 2 significant figures, so that's what we use here. We get 3.8 meters per second. Done. In another experiment, the ball is moving at 6 meters per second at the top of its arc. Calculate the speed of the ball at its lowest point. So this question, we're going to have to, whenever you get these kind of questions, when they say calculate the speed of the lowest point, we're going to have to use some conservation of energy. That's the most easiest way that I would do this question, using the conservation of energy. So what I would do is I would think of this as a floor. This is your base. So let me write its lines. Imagine this part here is your floor. The circles, this is the floor. And of course, your GPE here is going to be 0 because there's no height. And what about kinetic energy? Kinetic energy, of course, it's going to be at its max at the bottom. So kinetic energy at the bottom is going to be at its max. Of course, at the top, they told us that the speed at the top was what? It has some speed, so it does have some kinetic energy. So we're going to write has some kinetic energy, but it'll also have gravitational potential energy because we do have some height, which is 3 meters, doubling that. So by, conservation of momentum, adding these two must equal to adding these two here. So let's do that. So half mv squared plus mgh, so this plus that should equal to these two, because your gravitational potential is 0, so we're just not going to write anything. It's equal to your half mv squared, your velocity of your kinetic energy. And can you see how masses they all have mass? We can actually cancel mass from all of them. So we can write half v squared is equal plus gh equals half v squared. And so putting all your answers, your figures in there, so half, we know the velocity at the top, they told us was 6 squared, plus your g is 9.8, of course, and your height is 3 meters, because remember, that's a radius, which is 1.5, so it's 3 times, and it's equal to your half v squared. So calculating v squared, let's do that. So 3.5, 6 squared, plus 9.8, 3, by 2, taking the square root. That gives me to 2 significant figures, 9.7. That looks good. So 9.7. Now, next question. Question 9. It says a spring launcher is used to. Good. Yep. Question 9. A spring launcher is used to project a rubber ball of mass 2 kg vertically upwards. The arrangement is shown in figure 6. The ball is driven by a spring which is compressed and released. When the spring reaches the top at point X, alright, it's held stationary. Okay, so this is the uncompressed string over here. And so they put it inside this thing that when it springs, the spring is not still compressed because these things here are stopping it from fully being compressed to its normal uncompressed position. Say, but it's still partially compressed as the ball moves the launcher. Assume the spring has no mass. All right. The force distance graph of the spring is shown on which the lower and upper positions of the spring in the spring launcher are marked. Of course, so if there's uncompressed length, of course there's no spring. There's no, your force is 0. Your force for your spring force is going to be 0 because it's uncompressed. But when we uncompress it to the y position, which is what? It's 1 meter, which 1 meter is here, which is of course your y. It's going to be producing a 40 Newton force. And of course, when it goes over here, which is still being compressed by, again, 0.5, it is it's a 20 Newton force. All right, that's not too bad. Let's have a look at the question. Calculate the spring constant K of the spring. What a beautiful question. We know whenever you get a graph, a force distance graph, or like a compression graph, the K value is just a gradient. So what we're just going to do is calculate the gradient. So I'm just going to take, I always take the bottom one, which is 0, 0 normally, and this part here. So those 2 points, and I'm going to find y2 minus y1. So your K value, which is your gradient, is going to be your 60 minus 0. So just 60. 60 minus 0 divided by 1.5 minus 0. Let's see. That's just going to give me 60 divided by 1.5. And that gives me 40. Oh, sorry, let me write it here. 40 newtons per meter as your spring constant. Beautiful. B, calculate the change in spring potential energy of the spring as it goes from the lowest point to the highest point, x. Wait, you can actually do it in two ways, because we're given the graph and we know the area below the graph is your spring potential energy. It's that change in spring potential energy. But we can also do it, of course, by using the formulas, having a look at the figure here. So, but I think the most easiest way that I would do this question is by just looking at the graph. So calculate the change in spring potential as it goes from the lowest, so y, to the highest, x. So we want just the area under this graph here. We want the area of this whole point over here. Well, it's an actual it's a trapezium, and so using your trapezium formula, so area on the graph, gives SPE. It's actually a change in SPE. So that's the area on the graph. So it's going to be, area is just, so trapezium formula is half A plus B times height. So your A in this case can be any. So A, this is your B, and this of course is your height. So your A is going to be 20 and your B is going to be 40. So that's half 20 plus 40 times your height. So your height is 1 minus 0, so 0.5. Yeah, is that it? It's in meters. Good. So putting this in your calculator, you should get your energy, which is 15 joules. 15 joules. Oh, sorry, 15 joules. That's it. Wow. Yeah, using the graph really helps out a lot. 3 marks. Wow. Well, of course, you could have done it by hand. Of course, let's try also do it by hand to show you how it works. So what we're saying is we're going from point Y to X. So we're here and we're going to here. And we just want to find only the change in the spring potential energy. So what's the spring potential energy? Well, it's being compressed by 1 meter in this position at Y. So it's going to be, and it's going to have the most, of course. So it's going to be half K, which in this case we calculated was 40. Your change at X squared, which in this case was 1 squared, because that's your spring. You've compressed it by minus this over here when it's over here, which is of course half. Of course, your K value is 40. But now the spring is actually just compressed to 0.5, so 0.5 squared. And so looking at this formula here, we should get, and we get 15. Also, that works. That formula also works. But yeah, I would just use the actual, graph if it really helps, because it's much easier. Beautiful. C, so 4 marks. Wow. The spring with the ball is in place, is released from point 1. It moves up to X. So it moves up to X. All right. Shows this here, where it stopped and the ball is launched. Calculate the speed of the ball when it leaves the spring launcher. Show the steps involved in your working out. All right. Well, let's have a look here. This is the most easiest done by conservation of energy. So let's have a look at Y. When it's at Y, let's consider this the floor, the lowest point, which is the floor. Actually, let me a little bit move this down here. Let's consider this the floor. So, and can you see how at Y the ball initially is at the floor? So imagine thinking this as your GPE is 0 because there's no height. Your kinetic energy, of course, is 0 because it's held stationary at that point before it's like let go. But we know spring potential energy is actually at its max because it's being compressed the most at that point. So it's at its max. And again, we're using conservation momentum. Now let's have it here. Let's look here. Now, as the ball's over here, of course, we're going to get some gravitational potential energy because it is now at some height. So we're going to put just gravitational potential energy. Kinetic energy, of course, we're going to get, because now the ball has some velocity. It would have, yeah, given some velocity, and that's what we want to calculate. And what about the spring potential energy? Of course, we're going to get some still spring potential energy, as the thing is still, it was only uncompressed from here. It's still being compressed. It's still being compressed by 0.5 meters. So we also have some gravitational potential energy. So what do we do? Well, we equate them, because remember, this here should equal to this, because the total energy must be constant. So let's do that. So SPE must equal to kinetic energy plus your gravitational potential energy plus your SPE. All right. So your SPET is half, your K is 40. So at the bottom, we know it's being compressed by 1 meter. So it's going to be 1 squared is equal to your kinetic energy. So half your mass of the ball was 2, was it? No. All right, what was the mass of the ball? What is it? 2, yeah, 2. So the mass of the ball was 2, so we can put 2 there. Velocity squared, that's what we want to calculate. It's equal to your mgh, so your gravitational potential, so your mass is 2, your g is 9.8, and your height. So the height over here, remember we took this as the ground, so the height over here is just 0.5. Beautiful. The 0.5, so mg and h, plus your spring potential energy, so half, your k is of course 40, and how much was it being compressed? It was compressed still was compressed at 0.5 meters, so you square that. And so now we've got this over here. Of course, I think this is, I haven't written the formulas, to be honest. Because I already knew them in my head. Remember, it's just, let me write it in formulas too. So spring potential energy is just half K changing X squared. Kinetic energy is half mv squared plus mgh plus half K changing X squared. Same thing. That's what I've just done, and I've just written it now. And so let's calculate that. So this will be here. This will be 20 is equal to v squared. So what's the other one? So 2, 9.8, 0.5, 0.5, 40, 0.5 squared. That's going to give me 14.8. So velocity is equal to the square root of 5.2, which gives me so how many significance? 2 significance. So 2.3. So 2.3. So we'll go at 2.3 meters per second. So that'll be your velocity that the ball will be launched. And that's it. Is that it? Yes, it is for this part here. I hope you guys understood and learned something from this video. Please make sure to like and subscribe for more future videos, and share it with your friends who do this subject. And please, I hope you guys have a great day, and make sure to take care of yourselves, guys. Bye bye.